Time for us to do some problems involving parametrized curves, particles moving through space, with a bit of particular emphasis today on tangent lines. As always, it's important to do problems. The more that you do, the more skills you'll develop to help you solve problems further down the road. So if you're following along with the video, consider making use of the pause button. See a problem you like? Pause. Do it and see how far you can get. If you ever need any help, just unpause me and I'm there to help you out. Well, let's begin. Our first problem. Give a formula and name for the quadric surface on which the parametric curve and lies. So it's like, oh, so there's this curve somewhere in space moving around, but it's not moving around arbitrarily. It's on something. What something is it? That's what we need to figure out. So what do we have? Well, let's just see what we can do. We have the x-coordinate. It's e to the t sine t plus cosine t. The y-coordinate is e to the t, and the z is e to the 2t sine of 2t. Now, quadric surfaces. We've talked about those before. What do we know about our quadric surfaces? Well, if you look at the name quadric, it really says, look, you might have things which involve quadratic terms. So things like x squared, y squared, or z squared might enter into play. So we're keeping that in the back of our head. Now, looking at this, there's kind of a little tiny hint here. Notice this 2. That 2 right there. How do we think of that? You see, sometimes e to the 2t doesn't really mean e to the 2t. You're probably thinking, what? Are you sure? Well, what I mean is it can also be thought of as e to the t squared sine of 2t. We say, okay. So here, if you compare, the x and the y pieces have e to the t, but the z piece has e to the 2t. So it's very suggestive, saying, well, let's make them sort of look the same. So let's look at x squared and y squared. Now, y squared is the easiest, so we can do that. Y squared would be e to the t squared, which we can write as e to the 2t. X squared, well, square each part. That's e to the 2t. And then, sine t plus cosine t quantity squared. What would that be? Well, that would be sine squared plus the middle term, 2 sine cosine, plus the last term, cosine squared. Okay, well, what can we do? Well, one thing we can do is we can say, sine squared plus cosine squared. Okay, that we can do. That's great. Sine squared plus cosine squared equals 1. What about that other piece? 2 sine t cosine t. It sounds familiar, like we've seen it somewhere before. And there's sort of this other enticing thing, sine of 2t, and we say, ooh, that sounds familiar too. The bells are starting to ring. We say, 2 sine t cosine t is actually double angle formula, sine of 2t. So what does that tell us? Well, it tells us that x squared is e to the 2t times 1 plus sine of 2t. Okay, which we can distribute through. That becomes e to the 2t plus e to the 2t sine of 2t. Okay, all right. Well, now what? We say, well, wait. E to the 2t, y squared. All right. What about e to the 2t sine 2t? Z. So, we see that x squared is equal to y squared plus z. You can't tell. That really is a y squared. Or z is equal to x squared minus y squared. So we say, okay, here's a relationship between x, y, and z. Now, that is a quadric surface, if we think about, ignore where things came from. Because what we're really saying is that z of t is equal to x of t squared minus y of t squared. Not that z equals x squared minus y squared. This is a surface. We can actually talk about what it is. This is a paraboloid. Do you remember which kind? It's the hyperbolic paraboloid, also known as a saddle. And so, as far as the surface goes, it looks something along the lines of this. Now, of course, it's not that the parametric curve is the whole surface. What we mean here is that if you were to trace out the parametric curve, it sits on the surface. So it's doing something on this surface. We just can't tell, which part of the surface it's on, but it will always stick onto that surface because the formulas z equals x squared minus y squared is satisfied for every single point on the curve. And so that's it. That's the formula. That's the name. Of course, if we were being fancy, we would write down the hyperbolic paraboloid. That's the fancy name. So, all right, there we go. That's the problem. Good. Well, let's try another one. So, our next problem. Find the line in parametric form, which is tangent to the curve, x equals 2t squared plus t, y equals 2t squared, z equals t cubed minus t, at time t equals 2. All right, this is just another straightforward, hopefully nothing too surprising. What do we need? We need a point and direction, because we're looking for a line. Whenever we're looking for a line, we always need point, direction. That's sort of our mantra for finding lines. So what's our point? Well, to find our point, plug in time 2. So we would say at t equals 2, what you get, x is 2 times 4 plus 2. Well, 8 plus 2, 10. Y is 2 times 4, 8. Z is 8 minus 2, 6. Okay, now that was pretty straightforward. Plug in 2. Now, how about the direction? Well, for that, what we do is we say, well, think of this as a vector valued function. So 2t squared plus t, 2t squared, t cubed minus t. And now, call it r of t. Look at the derivative. And the derivative tells us how do things change. And so if we're understanding the direction that of the line is the way that we're changing. So the direction comes from the derivative. Now, of course, that's not the direction. That has t's in it. The direction is a vector. Not a vector valued function, just a vector. So we need to evaluate. So we plug in 2. R prime of 2. Well, 8 plus 1, 9. Then 8. 12 minus 1, 11. And there we go. So finally, we have our point, and we have our vector, and therefore we put it all together, and we're good to go. So we get x equals y equals z equals, because we are in parametric form, 10, 8, 6. So put that in, 10, 8, 6. And then 9, 8, 11. So 9t, 8t, 11t. And we're done. Good. That's it. Oh, that's great. We should have more problems like this, right? Well, we always have to have a couple warm-up problems. We want to build up. We want to be able to do the big ones, the hard ones. The harder they are, the stronger we get. Well, let's see where we go. So our next problem. The tangent lines to the curve, blah, 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 at times t equals 0 and t equals 1 are intersecting. Find the plane which contains both tangent lines. Okay, so we're after a plane. Well, what do? Well, we know that the tangent lines to our curve intersect. Now, that doesn't mean that they're the same line. Probably what's happening is we have something like the following. We have our three-dimensional space, and our curve moves through three-dimensional space in some way. I don't know how, but when we plug in at time t equals 0, we get one line. When we plug in at time t equals 1, we get another line. They intersect somewhere, we don't know where, but now we have two lines that cross each other. So if we have two lines which cross each other, there's a unique plane which contains those lines. Unless, of course, they are the same line, in which case there's infinitely many planes, but I don't think that's the case here. So what do we need? Well, whenever we're looking for a plane, we say we need a point and the normal. So, how do we get the normal? Well, let's work up to that. The point, usually that's not the hard part. So let's start by thinking about the tangent lines. So, what do we have? Well, we have this parametric curve. These are as points, but now we're going to do something very sophisticated. We're going to do a little doop and a little over here at the same time. Doop. See? Now we went from parentheses to these angled brackets, which means that now it's vectors. Vectors. Good. So we can do calculus with this. We like to be able to do calculus. After all, we're in a calculus class. We're pro-calculus here. So, what do? Well, if we think of this as our r of t, we look at our derivative, r prime of t. And what do we have? 9t squared plus 2, comma. What's the next one? Well, it'll be minus 1 minus 6t, comma. 12t squared plus 2t plus 3. All right, so that is our derivative at any given point. Now, how do we use that? Well, what we can say is that r prime of something, when we evaluate, is the direction vector of our tangent line. So, the direction vectors of our tangent lines, r prime of 0, r prime of 1. And what do we have? Well, plug in 0. We'll get 2 minus 1, 3. Okay, that's not so bad. Plug in 1. 11 minus 7. Whoa. And let's see, 12 plus 2 plus 3, 17. Okay, well, okay, sure. It's got to be something. So there we go. Well, now what? Well, these are the direction vectors for our line. So you can think of it somehow like, look, here's this direction vector, and here's this other direction vector. Of course, we can just move them down so that we can put them right there, right next to each other. Now, these two vectors are directions in the plane that we want. But we don't want a direction in the plane. We want the direction perpendicular to the plane. We say, cross product. See, cross product is a way to take two things and produce something perpendicular to both. We say, well, look, we want something which is perpendicular to both of these, so we'll cross, and that'll be what we want. So we're going to take 2, negative 1, 3, and we're going to cross that with the vector 11, negative 7, 17. So that's I, j, k, 2, minus 1, 3, 11, minus 7, 17. All right, I, minus 1, 17. So minus 17i, j times 3 times 11, 33j, k times 2 times minus 7, minus 14k. 11 minus 1 times k is minus 11k, but we're going in the other direction. So we subtract negative 11k, which really is add 11k. Minus 7 times 3 times I, minus 21i, but we subtract. So it's really plus 21i. And 17 and 2 and j is 34j, but we need to subtract it. So what do we get? Well, minus 17 plus 21, 4. 33 minus 34, negative 1. Negative 14 plus 11, negative 3. Now, let's check, because I've made enough mistakes with cross products over the years to know if we don't check, we probably got it wrong. But if we do check, we probably got it right. All right, so dot product, 8 plus 1 minus 9, 0, good sign. 44 plus 7, that gets us up to 51. Subtract 51, 0. Oh, good. So it turns out it's actually pretty clean. Now, this is our normal. Now, we're not done yet because we're not at the point where we have enough information. We have the normal, but remember, there's also the point. So how do we get our point? Well, we know it has to contain the tangent lines, which means it has to contain the points at time 0 and at time 1. So let's plug in at one of these times. I think 0 is probably the easiest. So at time equals 0, we get what point? Well, 0, 0, 2, and then 3, 0, 0, and then 0, 0, 0, 2, 3, 0. So now we have a point, and we have a normal, so we put it together. 4x minus y minus 3z, so these are our coefficients, is equal to, well, underneath we'll do a little bit of computation here. Plug in 2, 3, 0, so that'd be 8 minus 3 plus 0, which tells us we better get 5. Okay. And there's our answer. Good. Now, can we check? There's one other thing that we haven't used yet that should be true. If everything that they said is true, it also should contain the point at time equals 1. Let's just check that. So, what do we have at time equals 1? Well, 1 is also easy to plug in. 3 plus 2 plus 2, 7. 3 minus 1 minus 3, negative 1. 4 plus 1 plus 3, 8. So, if we've done everything right, it should be the case that when we plug this point into that plane, it works out. So, let's check. 28 plus 1 makes 29. Minus 24 does give us 5. It worked out. Woohoo! Now, you might be saying, hold on a second. We said they intersect, but we never found this point of intersection. Don't we need that? And the answer is no. They told us they intersect, and so we said, great. Now, we could have found the point of intersection and used that as our point, but the thing is, we only needed one point. It didn't matter where that point came from. So we said, hey, let's just pick our point from our point of tangency. So let's save ourselves some work. Oh, what a great idea. Saving ourselves work? I approve. Okay, so there we go. Now, let's try another problem. So here we go. We have two curves. So one of them, we'll call it R1 of t, 5t plus 2 log t, square root of 4 minus 2t minus t squared. And another one, R2 of s, which is 7 root 2 s to the 3 halves minus 4, e to the s squared minus 2s. Intersect at a point. What's the goal? We'll find cosine theta, where theta is the angle of intersection. And okay, all right. Even tells us, well, that says it's the angle between their respective tangent lines. So what's the idea here? What we have is we have our three-dimensional space, and we have some curves traveling through there in some very strange, curious fashion. So there's a curve there, and then there's another curve flowing around, doing something, and we're told they intersect. So they cross, and our goal is to say, okay, what happens? Well, if you zoom in on this, what will you see? What you'll see is that there's this intersection point, and then you get the following. There's one curve that looks something like this, and then there's the other curve, which is doing something more or less like that. And our goal is to find cosine of that angle. Okay, doesn't seem so bad. Well, there's a couple of hints right away about where we're going. First off, whenever we see anything that says find cosine theta, we said, hey, cosine theta showed up somewhere. And it's in the following place. Cosine of theta is the dot product, u dot v, over magnitude of u, magnitude of v. So, if we're ever asked to find cosine theta, we say, aha, we just got to figure out what two vectors we have to use, and we run it through this formula. So we've got to figure out the right pair of vectors. But in that sense, it's not too hard. We say, okay, the vectors are coming from the directions of the lines. So in other words, each pair of these lines has a direction vector associated with it, and so we're just going to grab those vectors. That'll be our u and our v. Okay, great, brilliant. Well, what's left? We've got to find those vectors u and v. Well, how do we do that? Well, we've got to take our derivative and evaluate at the right times. Well, how do we do that? So we're like stepping our way back. Okay, where do we begin? Where we begin is we say, where do they cross? Now, one of the things you might have noticed here at the very beginning of this problem is to say, hey, they are using different symbols. That's actually a nice convenience. They did that for our benefit because they want to say, don't think about the two different curves as having sort of the same parameter for time. They really have different parameters for time, and you want to keep track of that. So in other words, how I'm moving along here is more or less independent of how I'm moving along there. So what we have at the end is we're not sort of watching our particles move. What we're trying to do is to say, all right, we have this curve here, we have this curve here, and then we have to figure out where they intersect. So, well, when do things intersect? They have to be at the same place. So to find intersection, what we'll do is we'll set our coordinates equal. So we'll have to have that the x-coordinate, 5t plus 2, will have to equal the other x-coordinate, 7. And then log of t will have to equal root 2 times s to the 3/2 minus 4. And then we'll have to have the square root. 4 minus 2t minus t squared has to equal e to the s squared minus 2s. Okay, so we have to have all these pieces in play. Well, I see one thing that's easy to solve for. On the very first equation, we're told 5t plus 2 equals 7. Well, that's easy to solve. Subtract 2, divide by 5t equals 1. Which tells us that log of 1 is 0. Great. And it also tells us, what else? Well, here, 4 minus 2 minus 1 is 1. Square root of 1 is 1. So 1 equals e to the s squared minus 2s. Okay, that lets us say that s squared minus 2s is equal to 1. 0. E to the 0 is 1. Well, when is that true? It says potentially s is either 0, because that works, or s equals 2, because you can factor out an s times s minus 2. Now, do they both work? Well, let's just check it. If we plug in 0, we'll get square root of 2 times 0 minus 4. No. Okay, that one won't work. How about 2? Square root of 2 times 2 to the 3 halves. Well, that's like 2 to the 1 half, 2 to the 3 halves becomes 2 to the 4 halves, or 2 squared, or 4. And 4 minus 4 does equal 0, so that works. Good. So we have verified the intersection happens. And we know when. So we know time t equals 1 and time s equals 2. So our next thing is we say, okay, now that we know when the intersections happen, let's see what our tangent vectors are for each one of those times. So let's start with our first curve, r1. So if we compute r1 prime of t, do it entry by entry, 5, comma, 1 over t, comma, well, this is related to the 1/2 power, so 1/2, 4 minus 2t minus t squared to the minus 1/2, then multiply by the root of the inside, minus 2 minus 2t. R2 prime of s, okay, that would be what? 0, and that's easy. Then you have root 2 times 3 halves times s to the 1/2, and then the last one, e to the s squared minus 2s times 2s minus 2. And there we go. There are our derivatives. Now we plug in the right values. So our right values are the ones that we found. So for r1, which is to t, we plug in 1. So we have r1 prime of 1 is equal to 5, 1, and then, well, 1/2, 4 minus 2 minus 1 is 1 to the minus 1/2, and here, minus 2 is minus 4. Well, 1 to any power is 1, so that's good. So we end up with 5, 1, negative 2, 1/2 times minus 4. And r2 prime of s, which is 2, so we're plugging 2 in, will be 0. Then we have square root of 2 times 3 halves times square root of 2. Well, square root of 2 times square root of 2 is 2, and that cancels with the 2 downstairs, leaves us with 3. Then we'll have e to the 0. E to the 0 is 1. And then we're going to have 2 times 2, 4 minus 2, which is 2. And there we go. That's the other one. Okay, so now we're ready. Here we go. Move this up a little bit to give us some space. And we have the following. Cosine of theta is u dot v, so 5, 1, negative 2, dot 0, 3, 2, over the magnitude, 5, 1, negative 2, times the magnitude, 0, 3, 2. So the numerator, 5 times 0, 0, 1 times 3, 3, minus 2 times 2, minus 4. Divide that by the square root of 25 plus 1 plus 4, square each term, add it up, times the square root of 0 plus 4 plus 9. So that's negative 1 over, and here we'll get the square root of 30, here we'll get the square root of 13, and you can just combine them as square root of 390. And we're done. That's it. Well, that's actually not a very big number, which means that when they intersect, they're not exactly perpendicular, but they're getting kind of close to perpendicular. So whenever the cosine of theta is a small number, it means that you're close to a right angle. Whereas when it's close to a size of 1, that means that the vectors are either almost parallel or almost exactly opposite. So, all right, well, that's that problem. Good. Well, let's try some more, right? Of course. And Ooh, another angle problem. So the angle between a plane and a curve is found by taking the angle between the tangent line and the normal to the plane at that point of intersection. Find that cosine theta, where theta is the angle between the plane, where our plane, 3x minus 2y plus z equals -4, and our curve is, okay, well, that thing. All right. So what's going on here? Well, what's going on is that this parametric curve hits the plane somewhere. And our question is, how does it hit the plane? So we don't know, right? So there's this plane somewhere sitting out here in space, and our parametric curve, it's doing something. The cosine squared, sine squared, it's doing some crazy kind of behavior. But it's going to hit and pass through and keep going. I'm not sure how, but the question is, as it comes through, what can we say? Well, we need to find our angles, which means we need to find our vectors. And one of them is pretty easy. It says, look, the normal to the plane, that's one of your vectors. Great, perfect. What's our other vector? Now, as a reminder, why am I talking about finding vectors? So, when we see cosine theta, that's our u dot v, magnitude of u, magnitude v. So, all right, as they say, what can we do? What can we do? Well, let's just go ahead and read off our normal. So we're saying, look, we know one of them, it's a freebie, 3, -2, 1. The other one, we're gonna have to unravel this a bit. So first off, the question is, well, ultimately the big question is, what's the vector for the tangent line there? But in order for us to do that, well, we take the derivative and plug in the right time. But we need to know the time. So the question is, at what time are we there? That's what we need to know. So let's, first step 1. When do we hit the plane? Okay, so 1, when do we hit the plane? Well, for that, we say, look, we know x, y, z, so we'll plug it in. So we have 3 times 5 minus 2t plus cosine squared t minus 2 times 3 plus t minus sine squared t plus t squared plus sine squared t is equal to -4. All right, well, and again, where are all these pieces coming from? This is 3x minus 2y plus z equals -4. We'll distribute things out and start cleaning up. So this is 15 minus 6t plus 3 cosine squared t minus 6 minus 2t plus 2 sine squared t. Remember, the minus 2 goes to every term. And then plus t squared plus sine squared t equals -4. Well, okay. Well, this is going to be interesting here. Well, what happens here? We can notice a couple of things. There's 3 cosine squared plus 2 sine squared plus sine squared. Well, really, it's 3 cosine squared plus 3 sine squared. So if you put all of these pieces together, what comes out? You get a 3. So all those things together give us 3. Now, let's group by our degree. There's a t squared. All right. And now, there's a minus 2t and a minus 6t. Makes that minus 8t. And then we have 15 minus 6, which would be 9. And then what else do we do? Well, we need to add 4, which gets us up to 13, and add the 3 here, which gets us up to 16. All right, so t squared minus 8t plus 16, and that's going to equal 0 because we moved everything around. Well, that t squared minus 8t plus 16, that's beautiful. That's a perfect square. You see, it factors as t minus 4 squared equals 0. So it tells us, aha, t equals 4 is when we have the intersection. So we now know this intersection is at time t equals 4. Good, we found it. And one nice thing is we found one answer. You'll notice it said, well, don't find all the angles. It said find the angle. Well, if it had had multiple solutions, we'd be like, uh-oh, something's wrong here. But here, there was just one solution. And so that means life is good. Life is great, really. Okay, well, what happens next? Now that we know when we hit the plane, the next thing is to say, okay, step 2. What's our direction of our line at that time? And when I say that time, I mean the time when we hit the plane. So to figure that out, we need to take a derivative. So we have r prime of t. So taking our derivative, we have minus 2, comma, and the derivative of cosine squared t. Whoops, that's not a comma yet. I haven't finished taking the derivative of the first term. Minus 2 plus 2 cosine t negative sine t. Now, there's a comma. Then it's going to be a 1, and then it's a minus 2 sine t cosine t, comma, and then we'll have a last term, a 2t plus 2 sine t cosine t. Okay, there's our r prime. We can clean it up a little bit. Notice that we have 2 cosine t sine t or 2 sine t cosine t in there several times. Each one of those is actually something very clean. This is the same as sine of 2t. So as we're going through and simplifying, we'll just, for sake of space, we'll denote these as sine of 2t's. All right, we need to plug in our time. So we know our time is 4, so we're going to plug in 4. R prime of 4 is, well, minus 2 plus 2 sine of 8, comma, 1 minus 2 sine of 8, comma. And then the last one is going to be 8 and plus sine of 8. Whoop, there's no 2 here. I'm sorry about that. See, the 2 is part of the sine 2t. Okay, so it's negative 2 plus sine of 8, 1 minus sine of 8, and 8 plus sine of 8. Okay, all right. Good, good. There we go. Now, that is our other vector. You see, we already found one vector. There's our other vector. So, we have that our vector v is minus 2 plus sine of 8, 1 minus sine of 8, and 8 plus sine of 8. All right. Well, what's next? The next thing for us to do is u dot v. Okay, so what happens? U dot v. That's equal to, multiply here, 3 times the first term would be minus 6 plus 3 sine of 8. And then multiply the next term would be minus 2 plus 2 sine of 8. And the last term would be plus 1 times that, 8 plus sine of 8. Now, if we clean this up, what do we see? Well, we see the following. All right. Oh, whoops. I see another error I made. It's good we're catching them. You see this plus? I forgot to notice something here. This minus really should come out. So this isn't really a plus. It's really a minus. So we'll fix that. All right. And here, that means that this is a minus. And now, whoa, something amazing is about to happen. What do you see with the sine of 8s? Minus 3 sine 8, 2 sine of 8, sine of 8, all cancel out. Minus 6, minus 2, minus 8 plus 8, all cancels out. So we end up with 0. Well, it doesn't matter what the denominator is. The numerator is 0. These aren't 0 vectors. So we say, aha, cosine of theta is equal to 0. Well, what does that tell us? That tells us that the angle is perpendicular. Now, how does that fit into the picture? Well, it tells us that kind of something interesting is happening here. Most likely, we'd have to dig a little bit deeper, but most likely what's happening is the following. Since the tangent line has to be perpendicular to the normal vector, means that the tangent line's in the plane, which really says that our curve, which is coming here through space, probably just bounces off of the plane. That's what this is trying to hint at, right? So it doesn't cross at an angle, but somehow it just comes in, and so that here's our plane. It just matches. It's possible that it like the x cubed could do that, but usually that means more along the lines of it's a bounce off of the plane. Okay, well, all right, there we go. A lot of work for a 0, but you got to do the work because you don't know until you've worked through the process what happens. Okay, well, let's move on and let's try another problem. All right. Show the parametric curve given by the following, some expression. It has constant magnitude. And verify that r of t and r prime of t are perpendicular. Now, to say that something has constant magnitude, by the way, this is a little bit hard to see what this curve is doing, but here's the curve, and then it sort of dips behind there so that we can't see it very well, and then it comes back up. It more or less what the shape is like, if you're familiar with like a Pringle chip, you think about the edge of the Pringle chip. So you have it sort of coming up and down and back up and back down and returning to where you started. So that's what's going on there, is you have that shape. So you say, okay, all right, well, what does it mean to have constant magnitude? Well, it really means that this curve is sitting on a sphere. And so, okay, well, what do? We find the magnitude. And in particular, what we need to do is look at the following. We want to look at x of t squared plus y of t squared plus z of t squared. And we want to compute that. If that's constant, then our magnitude is constant. If it's not constant, our magnitude is not constant. It actually just simples down to a simple yes, no. What's happening with this expression? So, well, our first term, we have 1 minus sine of 2t squared plus root 2 times cosine t plus sine t squared plus cosine of 2t squared. So that's what we've got to work on. Now the first term isn't so bad. That'll be 1 minus 2 sine of 2t plus sine squared of 2t. Okay, that's not, like I said, not so bad. Then the next term will be 2 Then we square that. Cosine squared plus 2 cosine sine plus sine squared. Okay, and then the last term, that one's the easiest. Cosine squared. Okay, well, what's going on? Well, we see some things happen which are nice. We'll grab a different color here so we can mark. Cosine squared and sine squared, that'll be 1, which is great news for us. Woohoo! All right, well, what else? Sine squared 2t, cosine squared of 2t is also 1. All right, fantastic, beautiful. By the way, 1 is also 1. All right, well, that's kind of redundant. What haven't we done yet? We haven't done this minus 2 sine 2t and this 2 cosine t sine t. But now we're like, well, wait a second. Sounds like double angle because it's double angle. We say, look, this piece right here, this is a sine of 2t, and notice it's being doubled. So this minus 2 sine 2t and this 2 sine of 2t cancel. And everything else simplifies to 1, right? So we have 1, 2, 3, 4. Why 4? Because it's 2 times that. So 1, 2, 3, 4 equals 4. And we're done. That's it. And so, what can we say? Well, we can say that x squared plus y squared plus z squared equals 4. Take the square root, and we come to the conclusion that the magnitude of r of t is always going to be equal to 2. So, constant magnitude. So now we can say a little bit more than we had before. We can say, look, not only is it a constant magnitude, but we know that we're sitting on a sphere which has radius 2. All right, well, that's part of it. There's a second part. And the second part says, hey, remember we said something about constant magnitude, that r and r prime are perpendicular. Let's actually check that it's true. Now, that's not a proof that they're always perpendicular, but it shows you that, well, it works in at least one case. So let's work through this case. So we have r, so the next thing we should do is work with r prime. So what is r prime? Go through term by term. Go to the first term. Well, will be minus 2 cosine 2t. The 2 comes out by the chain rule, comma, and then we come here. We're going to get root 2, and the derivative of cosine minus sine. Derivative of sine plus cosine. Then come to the last term. Derivative of cosine 2t is minus 2 sine of 2t. Good. Progress. Great progress. Now, what do? Well, we now have r and r prime. Now we dot them. So, r prime dot r. Okay, what is that? Well, we just have to multiply the right entries together. So 1 minus sine of 2t times minus 2 cosine of 2t plus root 2 times root 2 makes it 2. We have cosine t plus sine t. And here I'm going to write it as cosine t minus sine t. Just that seems easier to work with. And then our last one, we have a cosine 2t and a minus 2 sine 2t, so that's minus 2 cosine 2t sine 2t. Well, we expand. Multiplying this out, minus 2 cosine 2t plus 2, minus 2 times minus there, that's why it's a plus, sine 2t cosine 2t. Now, our middle term, this is good. Look at our middle term. Cosine plus sine, cosine minus sine. What can you do? Well, if you expand that, you're going to end up with cosine squared minus sine squared. Now, why do we mention that? Well, cosine squared minus sine squared isn't just anything. That's cosine 2t. It's the double angle formula for cosine. Aha! Ha! Cool! So, this whole middle expression here, this cosine t plus sine t, cosine t minus sine t is cosine of 2t, and don't forget the 2, so plus 2 cosine 2t, and then the last part, minus 2 cosine of 2t sine of 2t. All right, good. Now, let's go and see if we get enough cancellation. Minus 2 cosine 2t plus 2 cosine 2t cancel. Great. Plus 2 sine cosine minus 2 cosine sine cancel. Everything cancels, and we're left with 0, and therefore we can conclude the dot product is 0. So r prime are indeed perpendicular. This is just a shorthand notation for perpendicular. We're done. We did it. Woohoo! The theory is true, which is great. All right. Well, on to some more problems then. Well, So, on to, a different kind of problem. A particle is traveling along a curve, which is parametrized in cylindrical coordinates by r equals t squared, theta equals t, and z equals 26t minus 6t to the 6. At time t equals 1, the particle leaves the curve and moves along a straight line, the tangent line. Where will the particle collide with the xy plane if it continues along the tangent line? Okay, now what's going on here? Well, if you think about what's happening here, it says the following. We're describing our location at any given time, but instead of describing it in terms of x, y, and z, we're describing it in terms of r, theta, and z. Now, is that allowed? And the answer is, well, yes, you can describe any way you like. It's perfectly fine to use a different type of coordinate system. So we say, okay, well, how do we make it work? So we say, okay, so instead of describing it in our cylindrical coordinates, we'll have step 1, start from cylindrical, move it to Cartesian. In other words, move it to something where we know what's happening. Now, there's a reason that we do this motion. You see, cylindrical coordinates are great for things which are nice and symmetrical around the z-axis, but they're not really set up for straight, flat things, whereas Cartesian coordinates are built off of straight, flat things. So we want to do our change. So our first step is to say we want to go from cylindrical over here and do it into Cartesian. Well, it's not as bad as it sounds because we know how to convert from one coordinate system to the other. So if we have r equals t squared, theta equals t, and z equals 26t minus 6t to the 6, that's a weird number, but okay, all right, whatever. What do we get? Well, we get x equals r cosine theta, which becomes t squared cosine t. Y equals r sine theta, which becomes t squared sine t, and z equals z. Well, that's easy. That's a nice thing about, it's nice when you're switching coordinate systems that says, oh, by the way, this one just stays as it was. Great. So that's 26t minus 6t to the 6th power. All right, good. Now we have our new curve description in Cartesian coordinates. It's not a different curve. In fact, it's the exact same curve at any given point. We're at the exact same point, but our description is into Cartesian because that's where our theory is set up. And so oftentimes this happens. It says, well, if you are trying to figure out how something works, switch it into a mode where you know how things work, and then carry out the computation there. So we say, well, we know how things are going to work. What do? Well, we need to figure out the tangent line, and we know it's the tangent line. It kind of tells us right here when it says it's the tangent line. It's a pretty good clue. Very, very strong clue. So we have, we'll call it r of t, just that's what we usually use to refer to our curves by. So we have t squared cosine t, t squared sine t, and 26t minus 6t to the 6. When we're looking for the tangent line, we also compute r prime. So, I have to do a little bit of work here. Product rule. Derivative of the first times the second plus the first times the derivative of the second. And similar here. Derivative of the first times the second plus the first times the derivative of the second. And finally, 26 minus 36t to the fifth. So we need to compute what's happening for the point. That's plugging 1 into the function, the curve, and the direction, plugging 1 into the derivative. So we have that r of 1 is, well, cosine 1 and sine of 1, and 26 minus 6, 20. Plug it into the derivative, r prime of 1. Well, it'll be cosine 1 minus sine of 1, right? Oh, whoops, we got that factor of 2. 2 cosine 1 minus sine 1, comma, 2 sine of 1 plus cosine of 1, comma, 26 minus 36, negative 10. Okay, so we've got our point and we've got our direction. Now we put it all together and we get our line. Okay, so we have x, y, z. So x is cosine 1 plus t times 2 cosine 1 minus sine of 1. And then y, well, sine of 1. See, how are we doing this? The x coordinate, then t times the x rate of change. Y coordinate plus t times the y rate of change. 2 sine 1 plus cosine 1. Then the z coordinate, 20 plus t times the rate of change. Okay. Now, we've got our tangent line. That's the way the particle moves. It's moving along that line. What are we looking for? Well, we're looking for a very specific thing. We're saying, where will the particle collide with the xy plane? All right, when do we hit the xy plane? The xy plane is also known as z equals 0. So we come along here and we say, okay, when does this equal 0? Well, I need 20 minus 10 times t to give 0. That says we're going to happen at t equals 2. So now we're almost done. We know what time. Now, when I say t equals 2, I'm not referring to the time for the original curve. That's been thrown out. The original curve is no longer part of the picture. I'm talking about the time in terms of our new tangent line. Okay, so we go through here and we plug in 2. And we just work through it carefully and every coordinate, one at a time. So for our x coordinate, we're going to get cosine of 1 plus 2 times 2, so that's 4 cosine 1. So that gives us 5 cosine of 1. And then there's going to be a 2 times this minus sine 1. So minus 2 sine of 1, comma. Then we're going to get a sine of 1 plus 2 times 2, which is 4 sine of 1. So that's 5 sine of 1, and then plus 2 times cosine, so plus 2 cosine of 1, and then for z, well, it's 20 minus 20 is 0, because we're on the xy plane. And that's our point. That's where our particle is going to hit the xy plane. So it's great. So this is actually, it's not so different. If you've been doing all the exercises, you might remember there was a problem involving an egg, and we released the egg and it traveled along. It's the same problem. The only thing that happened is we added this extra layer at the start. And the extra layer was, hey, we can describe things in different coordinates. And we say, well, that's fine. Give us the description in your coordinate system. We'll change it to our coordinate system and then proceed like we've did before. So, okay, good. Well, nice problem. They're all nice problems, aren't they? They're lovely problems. We're lucky to have such wonderful problems to work on. Okay, our next one. You have recently made it onto the newest reality show called The Ultimate Extreme Roller Coaster Happy Fun Hour. What a great show. I'd watch that show. You are currently in the second round. And in this round, there is a balloon filled with paint attached to the bottom of the roller coaster that you must detach by remote control so that it falls and hits a target. Okay, so what's happening here? Well, roller coasters move around in three-dimensional space. At least the fun ones do. It's not very exciting to go on a roller coaster that just goes back and forth in one dimension. So you can imagine it spinning and going all the way around. So here we go. This roller coaster moving all through space. And we can think of it as, just to simplify, we're just a little particle moving around. So that's the coaster as a particle. So what happens? Well, we say, okay, we keep reading. We want to hit the target. So as you wait for your turn, you watch you watch the contestants in front of you and cannot help but notice that if the target corresponded to 0, 0, 0, okay, so our target's the origin, then the position of the roller coaster could be described by t minus 8, t squared minus 5t minus 8, 48 minus t squared, where time goes from 0 to 6, the drop zone. You're very observant. Good for you. Okay, good. Now, neglecting gravity and wind resistance, because this is a reality show, at what time t should you release the balloon to hit a perfect bullseye? Okay, so what's happening? We're moving along, and we want to find that sweet spot so that when we drop it, it's going to move and hit the spot. Now, let's think about how is this geometrically? What's happening? So, what happens when you release the balloon? Well, the balloon, it moves in the same direction of motion it was going at the time of release. It's probably like a law of motion. Something continues to act in its current motion unless acted on by an outside force. So it just goes in a straight line. So we can think about this in a slightly different way. Say, look, I want to release it so it flows along its tangent line. Well, what do I need to have be true? I need to have it so that that tangent line goes through the origin. So here's our stated goal. Our goal is find time t so that the tangent line goes through the point 0, 0, 0. Okay, so that's what we're after. We're after a time where our tangent line goes through the origin. Now, we have to think about, well, how do we know if our tangent line goes through the origin? Well, it goes through 0, 0, 0. Let's think about what our tangent line would look like. So let's sort of say, we'll pick all the tangent lines and then focus on just the right one, right? That's a good philosophy. If you're looking for a particular line, find all the lines and then say, which one is just right? Just right. Okay, Now, let's think about what's happening. So let's think about, we have this, we're going to convert this into a vector value function. So we're doing a little bit, doop, doop. See, we made it vector value. Aha! Now we're like, calculus, we can do it. Yeah! All right, so we have our r of t is equal to t minus 8, t squared minus 5t minus 8, and 48 minus t squared. And our prime of t, since we need our tangent line, will be 1, 2t minus 5, and minus 2t. So let's find our tangent line at A. So our tangent line at time t equals A, well, how would we write that? X equals, y equals, z equals. Well, we would have, I'm going to plug A into here. So A minus 8, A squared minus 5A minus 8, and 48 minus A squared. Okay, that's our point. And then plus, now plug into here, we have 1 times t, 2a minus 5 times t, and minus 2t, sorry, minus 2a times t. So I've plugged a into r prime, 1, 2a minus 5 minus 2a, plugged a into there, and there we go. We need to pass through the origin, which means we need to have all these equal to 0 simultaneously. So what we need to do is figure out, when is this true? And if we do that, then we're done. We've succeeded. All right. Now, we have two things to solve for. We need to solve for A and for T. Well, actually, which one do we really care about? Well, the one we really care about is A. You see, that's the tangent line at the time when we release at time A. And that's what we're after. We want to know the time to release. So our goal is find the A. Okay, well, here we go. Our first equation, A minus 8 plus T equals 0. Now, again, this is so, this is a case where you have to be careful and sort of disassociate the T here with the T there. I'm going to go ahead and this one time make it really clear. So I'm going to replace these T's by a different symbol. We'll use the symbol tau, just so that we don't confuse ourselves and say, well, wait a second, don't you mean something else? So tau is for our tangent line, T is for when we're on the track. Oftentimes we won't distinguish these two, we'll just use the symbols interchangeably, but it can lead to confusion if you're not careful. And we don't want to be more confused than we need to be. Okay. So what do we have? Well, we can come here and we can say what? I can rearrange this and say, I'll solve for tau. So tau is 8 minus A. All right, great. Well, now what do I do? Well, now I plug tau into one of these equations. Let's plug into the bottom one. So I'm going to plug it into there. So 48 minus A squared plus minus 2A, whoops, my handwriting is so bad I can't read it, minus 2A times 8 minus A has to equal 0. Well, that would be minus 16A plus 2A squared. If you multiply that out, then you have a minus A squared and a plus 48. Okay. All right. Well, we combine, equals 0. That becomes A squared minus 16A plus 48 equals 0. So what are we looking for? We're looking for two numbers that when we multiply them together, we get 48. But when we add them, we get 16. Well, 48, what can you do? 6 times 8? No, that's not going to work. 24 times 2? No, definitely, that's way too high. 4 times 12? Yeah, that's the one. So this becomes a minus 4, a minus 12 equals 0. We say, aha, that gives us candidates. A equals 4, a equals 12. Now, which one is right? Well, we're told, remember what A is. A is the time we release. We're told we have to be between 0 and 6. So it can't be 12. That leaves us with one candidate. Now at this point, we could say, okay, the answer is 4. And we'd be probably right. If we were cautious, what would we now check? Well, we would say, look, we know A equals 4. We can talk about tau. That tau would be 4 as well. And the cautious version of us would say, we should verify this third equation. Because we really use the first and third equations to make it work. We should check the middle equation. So, let's see, 16 minus 20 minus 8. What would that be? Well, it'd be negative 12, right? 16 minus 20 minus 8. Yeah. And here, 2a minus 5, that would be 3. 3 times 4 would be 12. Negative 12 plus 12 is 0. So all the equations work. So we truly do pass through the origin. So our answer is 4. And we're done. Because, well, what were we after? We were after at what time t should we drop? So if we drop at exactly 4 seconds, we'll exactly hit the bullseye. Good. Now, you might say, Steve, what about the hint? You never read the hint. Oh, okay. What does the hint say? To hit a perfect bullseye, what must be true about the relationship between r and r prime? Well, what is the relationship between r and r prime? If you think about the tangent line, well, we'll make a little note up here in the corner. Our tangent line looks like the following. It looks like I'll say r of a plus some multiple r prime of a. So that's our tangent line. Now, if we want it to pass through the origin, it has to mean that 0 has to be a point of our tangent line. So we really say, look, 0 has to equal r of a plus tau r prime of a. And what does this mean? Well, if you rearrange it, it says r of a is equal to minus tau r prime of a. And in essence, it says, aha, r of a has to be parallel to r prime of a. That's one of the things that it says. And of course, what you really do is you come to here and you say, look, here's a system of equations. If you solve that system, you'll find it. Well, guess what? This system of equations is exactly this system of equations. So we actually did the hint. We just weren't really explicitly saying what we were doing. So that's what's going on. Okay, good. Wow. Hopefully someday we can get onto that show. Ultimate Extreme Roller Coaster Happy Fun Hour. We'll do great. We'll be fantastic. You know, people say, calculus, does it ever have any real-world applications? Here's a real-world application. Winning reality TV shows. Good stuff. All right. On to our next problem. You have constructed a track which follows along a parametric curve, t cubed, 6t squared minus 18, 9 minus 3t, where time runs from negative 5 to positive 5. Away from the track, there is a cable located on what corresponds to the z-axis. So maybe we should start drawing things. So we have our cable here. So here's our cable. And we have our track running along here. So The track is doing something, I don't know what, but it's moving along in space. Well, now what? You send a car with a laser pointer attached down the track. All right, so a laser pointer. Now, the nice thing about a laser is it shoots this infinite beam in a straight line. Doo! And, okay. And as the car moves along the track, the laser pointer sends a beam of light along the tangent line in both directions. Oh, it's like a two-sided. So it goes. So essentially what we have is we have this tangent line moving down the curve. That's cool. All right. Determine the coordinates corresponding to the point, or possibly points, on the cable which will be hit by the laser beam as the car goes down the track. So, in essence, as the car moves, so here's our little car, we have a tangent line. And so we move along, and at certain points, as we move along, we might hit that cable. We might not, who knows? But that's our goal. So it's like we have all these tangent lines moving down. And our goal is to say, okay, let's find all the times when we hit the cable. Well, let's think about our process. Our process is, let's list all of our tangent lines. And then we'll figure out which ones are nice. So we have our curve that's given to us. R of t is t cubed 6t squared minus 18 and 9 minus 3t. Our prime of t, okay, take our derivatives, 3t squared, 12t, negative 3. All right, now that's our position, there's our derivative, and so our tangent line at some time, we'll say at time t equals a, we just need to specify time, so I'll just say a, is what? Well, it'll be x equals a cubed, y equals 6a squared minus 18, and z equals 9 minus 3a. All right, so there are the coordinates, and then plus, plug in our a into our derivative, 3a squared times t, plus 12a times t, and plus negative 3 times t. Now, all right, there we go. Similar to the last problem, some people start to confuse the t's because there's the t's that are part of the tangent line, and there's the t's that are part of the parametric curve. We just so often use t to represent just the parameter. But whenever you have separate curves, so the tangent line is its own curve, they really should be thought of as independent. If you're not comfortable with that, introduce a different symbol. So let's suppose we don't use t. Let's switch up. Let's use a symbol. Let's say s. Okay. Now, all right, we're a little bit more safe. Okay, that way we definitely won't confuse t and s because they're different. Okay. Well, what do we need? We need to hit the cable. The cable is on the z-axis. And there's a nice hint. Points on the z-axis are of the form 0, 0, z. Say, hey, perfect. That tells us something. It tells us that we need x to be 0 and y to be 0, and z can be whatever it needs to be. So we now have a plan. We have two equations and two unknowns. So we need to figure out what are a and s. And we really do need a and s because that'll help us find our z. So let's see what we have. In the first equation, what can we do? Well, if you look at the first equation, notice what do they both have? You have a cubed, there's a squared. Lots of a's. Let's pull it out. So I have a squared times, then it'd be a plus 3s equals 0. Now in the second equation, well, nothing really quite so clean. you'd have 6a squared minus 18 plus 12 times a times s equals 0. Let's look at our first equation. A squared times a plus 3s equals 0 says there's really two possibilities. And what are they? Well, one possibility is that a equals 0. Okay, let's check. Does that work? 0 minus 18 plus 0. Does that equal 0? No, it equals minus 18. So this would imply minus 18 equals 0, which is not possible. Okay, so that means it's not the case that a equals 0. We can rule that out. So it is the case, then, that a plus 3s is equal to 0. So we say, all right, a should equal minus 3 times s. All right, now that will help us. So let's take that and plug it into our second equation. So minus 3s squared would be 9. S squared times 6 would give you 54s squared. Minus 18. And here, minus 3s times 12a, 12s, right? Because a is minus 3s, would give you minus 36s squared. All right, that's equal to 0. And wow, this is actually working out really nicely. 54 minus 36, 18s squared. Move the 18 across equals 18. Well, the 18s cancel. S squared equals 1. Brilliant. That says what? It says S is either plus 1 or minus 1. Great. All right. Now, what do we go from here? Well, now that we know S, we say, look, here's our possibilities. What are they? We could have the following. S equals 1. Okay, if S equals 1, A would equal negative 3. So that says A equals negative 3. So we now know S equals 1, A equals negative 3. What are the points? Well, 0, 0, because they were set up to be 0 and 0. And now we plug them in. Since A is negative 3, we're going to get 9 minus 3 times negative 3. Well, that really makes 18. And then have minus 3 times 1. So 18 minus 3 makes it 15. Okay, plugging in, A is negative 3, 9 plus 9, then minus 3. All right, so that's one of our points. Now we do the negative 1. If S is negative 1, well, A is negative 3 times that, so that says A is equal to 3. So plug it in. 9 minus 9. 0. Gone. All right. Negative 3 times negative 1. Positive 3. So we end up with 0, 0, positive 3. And that's our second point. All right. And there we go. We found there are going to be 2 points where that laser hits the z-axis, and the coordinates are 0, 0, 15 and at 0, 0, 3. Great. Beautiful. Beautiful. That's a nice problem. Well, as of course all problems are, which makes you want to keep going. So let's do one more. One last problem to finish it up. One last problem to find them all. So, suppose we have the following. H of t is this incredibly long thing, cross product, another incredibly long thing. Wow, God. And what do we want to find? We want to find h prime of 0. Oh my gosh. Oh, oh, this looks, oh my gosh. We're going to be here for a while. That's all right. Now, let's back up a little bit before we panic too much. You see something like this and you're like, oh, it's gonna take us forever. But let's think about different ways we can approach it. And let's find one that won't take us forever. That's preferable, right? We don't want to take forever on an exam. We want to take the right amount of time. So what's really going on here? I have two functions here. So I have one function, I'll write it out, is sine t plus 2t plus 2, comma, e to the minus 9t minus 4 cosine of t, comma, t cubed plus 6t. And I'll have another function, which I'll write. I'm going to give myself some space here, g of t. And what is that? Well, it's 1 plus arctangent of t, comma, 7t to the fourth plus t minus 3, comma, and 2 cosine of 5t. Okay, so those are our two functions. What do we want to do with them? Well, it says take the cross product, and that produces a new function. Okay, so we could do the following procedure. Step 1, take the cross product of two functions and produce a new function, which is going to be huge. And then it says take the derivative, right? Because we want to find the derivative. So it's like, okay, now we have this massive thing and we take a derivative. There's going to be a ton of product rules everywhere. Like, you get a product rule, you get a product rule, and it's going to take us a long time. We're going to have to go through multiple sheets of paper, and then we plug in 0. Now, that seems to be the way to go. Or is it? Okay, the answer is we're actually evaluating. Now, you might say, yeah, Steve, we are. We're plugging in 0. That's our last step. I know that. But here's the thing. When you're evaluating, you should always ask yourself the question, when should I evaluate? Now, the answer to the question is as soon as you can, but not sooner. Now, you might say, no, Steve, the right answer is always evaluate at the end. That's what we always do. We always evaluate at the end. And you can. That's not wrong, but it almost always involves more work. And as much as I like doing more work in the right setting, I also enjoy taking care of myself. You know, after all, we love ourselves enough to take care of ourselves. So, what am I trying to hint at? Let's think about what we can do to make our life easier. So we have the following. H of t is, I'm going to write it right now just for shorthand, f of t cross g of t. So let's just say what we know. We're going to take the derivative at some point, and we have a product here. So we can say, look, h prime of t, according to product rule, the derivative of the first, cross the second, and then plus the first cross the derivative of the second. All right. Great. Good. Beautiful. Well, now what? Well, you might say, okay, so now we have to take all these cross products. But wait. We want to know what happens at 0. So here's the idea. H prime of 0 is f prime of 0 cross g of 0 plus f of 0 cross g prime of 0. So here's the moral. We can do all our cross products first and then evaluate, or we can evaluate and then take cross products. The thing is, if we take our evaluation first, instead of having to deal with these kinds of expressions, we have to deal with these kinds of expressions. In other words, whoosh, it's a lot simpler to take the cross products. So let's simplify from the start. So here's our plan. We're going to find these pieces, f prime of 0, f of 0, g of 0, g prime of 0. And then we're going to take our cross product. So let's step back to our functions. We will have to take derivatives of them both. That's unavoidable. But let's not do anything with the cross products just yet. Okay, so what is f prime of t? Well, we go through term by term. Cosine t plus 2, comma, minus 9, e to the minus 9t. Then it'll be plus 4 sine t. And then we'll have 3t squared plus 6. Okay, that's the derivative for f. What's the derivative for g? Well, derivative for g, that would be g prime is 1 over 1 plus t squared. Arc tangent. What a beautiful thing. Then 28 t cubed plus 1. And finally, it'll be minus 10 sine 5t. Okay, so we took the derivative of each piece. Now remember, our goal is evaluate before we take cross products. So let's go through and evaluate. What do we have? Well, plug in f of 0. We get 0 plus 0 plus 2. 2. E to the 0 is 1. Minus 4 is minus 3. And then 0 plus 0 is 0. Okay. F prime of 0 is 1 plus 2, 3. And then minus 9 plus 0, minus 9. And then 0 plus 6, 6. All right. How about our g? Well, let's do that too. G of 0. 1 plus our tangent of 0. It's 1 plus 0. 1. 0, 0, minus 3. 2 times cosine 0 is 2. G prime of 0. Well, 1. And then here, we're going to get 28 times 0 plus 1. 1. And then minus 10 times 0. 0. Okay, 1, 1, 0. You'll notice what cross products we have to take. Well, our cross products aren't the long expressions of functions. They're just numbers now. So we come back and we say, let's update. What do we have? Well, f prime is 0. 3, negative 9, 6, cross. 1, negative 3, 2. Plus, I ran out of space, f of 0. 2, negative 3, 0. Cross. 1, 1, 0. All right, so we only have to do 2 cross products. But wait, if you act now, we'll throw out 1 cross product for free. Now you're like, whoa, what a deal. What do we have to do? Tell me more. Look at the 2 cross products. I claim one of them is a freebie. In other words, you don't have to do anything. It's automatic. You're like, what? Which one? Why? Where? Well, look at the first pair. 3, negative 9, 6. 1, negative 3, 2. What's true about that? These 2 vectors aren't the same, but they're almost the same in that if you scale the second one by 3, you get the first one, which means that they point in the same direction. But one just goes 3 times further, so it's just... What happens if you take the cross product of parallel vectors? Do you remember? It's one of the fun things about cross products. Remember, the dot product of perpendicular vectors is 0. The cross product of parallel vectors is also 0. So, because these are parallel, this is going to equal 0, 0, 0. So, we've now reduced to saying we have to do just 1 cross product. 1 cross product to finish it off. Wow. So, it looked at the beginning like we were going to have a cross product nightmare. But at the end, it says, hey, the only cross product we have is the following 2 vectors. 2, negative 3, 0, and 1, 1, 0. And look at those zeros. We like it when there's lots of zeros. Because why? I times negative 3 times 0 is 0. J times 0 times 1, 0. K times 2 times 1 is 2k. 1 times negative 3 times k, minus 3k, but we're going the other direction, so add it. 1 times 0 times I, 0. 0 times 2 times j, 0. So we end up with 5k, which tells us that our final answer is the vector it's 5k. So it's not at the start, it's at the end, 0, 0, 5. And that's it. That's it. We'll do this a couple more times throughout our various practice sessions where we have like, here's this terrible thing. It's going to be a nightmare for us. Oh, wait, we're evaluating. Let's think about moving our evaluation up earlier in the process. Now, you can't move it up too early. You'll probably like, ooh, this is cool. I'm going to do this all the time. You can definitely look for opportunities. But for example, I couldn't have started this by saying, let me plug 0 in right away and then take a derivative. Well, no, you would have gotten 0 out. So you can't just plug in 0 and start. You have to say, well, where can I plug it in? The answer is you can plug it in once you don't have to do anything else, which uses the t's. In this case, we could plug in once we were done with derivatives. So that's why we took our derivative first, and then we evaluated. All right, so something to look forward to, some foreshadowing of sessions to come. Well, thanks for hanging in there, and see you again. Have a great day.